We're starting sections 13.1 and 13.2, vector valued functions, and we're going over scalar and vector functions, parameterizing space curves, calculus of vector valued functions. So what is a vector valued function? A vector function or a vector valued function is a function whose output is a vector. And we saw a few of them in transformation section. For example, a vector function R from R real numbers to R3 has the form R of t equal to f g h of each of them, f of t, g of t, h of t. That's the ith component is f of t, j component is g of t, and k component is h of t, where the independent variable t is the scalar in R, and the dependent variable r of t is a vector in R3. The scalar functions f and g and h are the components of the vector. Now, let's give an example. Let's example 1, r of t is equal to cosine t, sine t, and 1. What is this? Well, if I was going to just ignore the third component in here, I would have come up with basically only sine of t and cosine of t. So if I just had this parameterization you've seen before. You've seen cosine t and sine t. And that parameterization gives you the circle. Now, here is not that though, it has another component in it, and that's the 1 for z. But 1 for z means that z is equal to 1 for all of these values. That means that whatever you're doing, the parameterization that you're doing sits in z equal to 1. And then, so you get the circle up there, and then the basically it's going to sit in z equal to 1. So what's the domain for this? I can plug in any t in here, right? And if I can plug in any t in there, the domain is going to be the entire R. How about the range? The range is going to be this nicely drawn circle over here. So this is the range of this function, because it's all the points that are in the 3 dimension that can be it can be in the image of R. Now, so again, for every values, you can see that for every value, the position vector goes around and around for different values of t. Now, what does it mean for limits and continuity for vector functions? Again, vector function has multiple components. There's ith and jth and kth components, and let's think about the vector function that goes from R to R3. The limit of R3 as t approaches a is defined component-wise. So if you're thinking about, because I have to define the continuity through limits, right? And so the limit of R of t is just limit of the first component, limit of the second component, the limit of the third component. And that's how we find the limits for R of t. And so therefore, R of t is continuous at a if f and g and h are all continuous. So now that we're saying that each limit of the entire thing is just all limit of each component separately, put together, that means that each component, if they are continuous, then the vector function is going to be continuous also. Now, example 2. The components of the vector function r of t equal to f of t, g of t, h of t is equal to t and natural log of 1 plus t and 1 over t minus 1. So in this case, you can see that if each component is an elementary function, so each component is continuous within its domain. Now, if each component is continuous within its domain, if I find all the domains and find the intersection of all of them, then I can find the domain for this r of t. So the domain, because it comes again from the components. Everything is component-wise. And so the first one, t, the domain of t is just negative infinity to infinity. Natural log of 1 plus t is anything that makes the inside, so anything that makes the inside bigger than 0. And that is t is bigger than negative 1. For the last one, anything that does not make the denominator 0, so you have to exclude 1. And so you get this. And if you put all of these on a number line, you see there's a negative 1, and there is 1, and we know that from 1 to infinity, so one domain goes from negative 1 to infinity, so we're throwing away all that. And then the other domain excludes 1, so everything that is excluded you take out, and negative 1 was already excluded, so what is remaining is negative 1 to 1 and 1 to infinity. And R is continuous on this domain because all of the components are. So I click a question 13.1a. Find the domain of the vector function r of t equal to t to the power 8 and square root of t minus 1 and square root of 9 minus t. And I say pause for a minute and then come back and see the answer. So hopefully you paused. Let's see. What is the domain of t to the power 8? That's negative infinity and infinity. What is the domain of that? That's t minus 1 bigger than 0. That's t bigger than 1. What is the domain of that? That's 9 minus t bigger than 0. Therefore 9 bigger than t. Therefore t less than 9. So if I put everything on the number line, I'm excluding every t bigger than 9, everything, here's this small error over here. These are all bigger than equal to, and so I'm excluding everything bigger than 9, everything less than 1, and so I end up with 1 and 9.